Hello and welcome back to Algebra 1 with Miss Betsy. I'm very glad that you are along with us today as we continue our discussion on graphs of straight lines and equations of straight lines. We're going to talk about a specific relationship in linear functions today, and that's called a direct variation. Before we do that, however, I have our final piggy lame joke, and I know some of you are just snorting with happiness over that. Why did the piglet eat 3 whole pizzas? Well, he was trying to make a hog of himself. So if you're tracking with me, we are in section 6.9 of my text, which is Algebra 1 for Christian Schools, published by Bob Jones University Press. It's the 2nd edition. As always, you can use any standard algebra text and gain value from this lecture. I'm on page 258 in my book. And we're talking about something that they call direct variation. And direct variation is a linear function in which one variable is a positive multiple of the other variable. So let me go ahead and write this down here. If I have this chart of ordered pairs, x and y, and if x is 0, y is 0, if x is 1, y is 4, if x is 2, y is 8, if x is 3, y is 12. What would come next in our progression? 1 times 4 is 4, 2 times 4 is 8, 3 times 4 is 12. If x was 4, y would be 16. And what we have here is a collection of 5 ordered pairs, 0, 0, 1, 4, 2, 8, 3, 12, and 4, 16, where one variable is a positive multiple of the other variable. The y is 0 times 4 times 4 times 4 times 4. So y is a multiple of x, where the multiplier is 4. And this is something where there's a consistent relationship between the x and y. As the x value gets bigger, the y value gets bigger. Now they're not getting bigger at the same space. Like x is just going up 1, 2, 3, 4. Well, y is going up 4. 8, 12, 16, but there's a direct relationship between them. Every proportionality that they increase, if x goes up, y goes up by a multiplied value. If x decreases, y decreases by that same multiplied value. And this is what they call direct variation. And there's another type of variation that they, an example of direct variation would be, in general, if this is the amount of time that you're studying your algebra, this is about the understanding that you have of algebra. You're not going to gain it. But as your study time, which might be your x value, increases, your understanding, which might be your y value, is going to increase as well. The more you study your algebra, the more you learn about algebra. The more time you spend visiting with a friend, the better you get to know your friend. The more time you spend studying God's Word, the more you know God. There's a direct relationship between one thing and another. It's what they call cause and effect. The more you study, the more you gain. The less you study, the less you gain. There's also something that they call inverse variation, and that's where as one variable goes up, increases, the other variable decreases. So there's sort of an upside down relationship between the two. We're not going to talk about inverse variation though. We're only talking about direct variation in Algebra 1. And there is a formula that they use in the general equation of direct variation. Just like we have the general equation of a straight line, it is ax plus by is equal to c. We have the slope-intercept form of a straight line, where you say that y is equal to mx plus b. The formula for direct variation is y is equal to kx, or the equation for direct variation. And the k right here, this is very special. This is what they call the constant of variation. The constant of variation is simply that multiplier. Let me go ahead and do this again. 3, 4, 0, 4, 8, 12, 16. What's our constant of variation here? Constant of variation here would be 4, isn't it? Remember, that constant of variation is what you're multiplying by. So if you had the relationship that we have here, it's a function because for every x, there's only one y. That's why they say it has to be a linear function. For every x, there's only one y. The constant of variation here would be 4. So the equation for which these ordered pairs as a solution is simply y is equal to 4x. Okay? Now, there's something else that I want you to notice. Let me look at my book. Okay. Y is equal to kx. Does that make you think of anything? Well, it is sort of like our equation of a line when it's in a slope-intercept form, isn't it? Y is equal to mx plus b. This right here is direct variation, while the second equation right here is the slope-intercept form of a line. And they're very, very similar. What do you notice that's different? Well, yeah, the letter's different, but that's not what I'm talking about. This is our slope, this is our intercept. What's our intercept over here? No, don't tell me there isn't one. The y-intercept over here is at 0. What does that mean if the y-intercept is 0? Well, think about what our Cartesian coordinate system looks like. What's that intersection right there at the middle where they cross? That's called the origin. And what are the coordinates of that point? That's right, they're the point 0, 0. So the y-intercept is 0. So anytime that you are graphing a direct variation, every single one of those, are the graph of the line is going to go through the origin, and I'll illustrate that for you in a minute. This right here is direct, it represents direct variation. This is the equation that we've learned to recognize as the slope-intercept form of a line. Now let me show you a difference in an expression that represents direct variation and one that does not. If y is equal to kx is direct variation, then y is equal to 2x. Okay, you can say y varies directly as twice x, or y varies directly as x. Y is equal to 2x. This is direct variation. Y is equal to 2x minus 3. Y is equal to 2x plus 1. Yes. No. No. Why? This represents a direct variation. These two don't. Why not? Because for it to be direct variation, the y-intercept has to be 0. It has to pass through the origin. Y-intercept here is -3. Y-intercept here is 1. So it's going to be very easy for you to take pieces of information and put it into the form of a line, because the y-intercept is always going to be 0. when you have direct variation, which means that the only thing that you're going to have to worry about is the slope of the line, and the slope of the line, when you graph it, is the constant of variation. That looks like a KU. Y is equal to KV. K is our constant of variation, which also, when you graph it, ends up being your slope. So let's go ahead and look on page 259 if you have the same text as I do. And this tells us, the question here is, the perimeter of a square is directly proportional to the length of one side of the square. What is the constant of variation? Okay, what does our perimeter of a square, what is our perimeter of a square? Think back to that formula. The perimeter of the square is equal to 4s, isn't it? It's 4 times the side, because with a square, all of the sides are the same dimension. That's not a perfect square. It's not like the sides aren't all the same length, but on a square, all 4 sides of that square are identical. And the perimeter of the square is 4 times the side. So this right here represents a direct variation that says the perimeter of a square, perimeter, is directly proportional to the side. What is the constant of variation? The constant of variation, remember I said, was the multiplier. So do you see how this fits our equation for direct variation? Y is equal to kx. What value do we have for y? We have p. What value do we have for k? We have 4. What value do we have for x? We have s. The relationship between the perimeter of a square and the sides is that of direct variation, because we have this multiplier here. Our constant of variation is 4. So now let's go ahead and look at example 1. Now, hang in here with me. Some of this vocabulary sounds really strange to you because you've not heard it before. Do not be afraid of it, okay? Number 1 says, read the table. Is y a multiple of x? Well, I guess there should probably be a table up here for us to read, because not all of you have your books. 0, 1, 2, 3, 0, 7, 14, 21. That is one crooked table that I've done, isn't it? Read the table. Is y a multiple of x? 0 times 0. 1 times what is 7? 1 times 7 is 7. 2 times 7 is 14. 3 times 7 is 21. So yes, y is a multiple of x. And see here, we have our 0, 0. Again, remember, I told you that the y-intercept, because we have y is kx, the y-intercept has to be 0. And that the graph of this line is always going to pass through the origin. You see this because if x is 0, it doesn't matter what you're multiplying by. You're always going to end up with a value of 0 for y, because 0 times anything is equal to 0. So this that little fact right here that you learned a long time ago, that 0 times anything is nothing, that's why with direct variation, you're always going to be going through the origin, because if x is 0, y has to be 0 as well. And yes, this right here does have 7 being the multiplier. The next question is, what's the constant of variation? Remember I said the constant of variation is that multiplier. So if they're asking you what the constant of multiplication is, the constant of variation, you would say k is equal to 7, because k is the constant of variation. You have to learn the vocabulary. Constant of variation. Now, we've read the table, we've seen that y is indeed a multiple of x. It's multiplied by 7. We see that the constant of variation is 7. What's our next question? Write an equation representing or expressing the relation. Well, what's our form say? It says y is equal to kx. What is k equal to? K is equal to 7. So y is equal to 7x. This is the equation, y is equal to 7x, that represents the relationship that we see here illustrated and satisfied by these 4 ordered pairs. If I told you to go and graph this on grid paper, you'd know exactly where to do it. Where's the y-intercept? It's 0. So you start at the 0, the slope is 7, you kind of 1, 2, 3, 4, 5, 6, 7, move 1 to the right, and you have a very steeply sloped line that is the pictorial representation, the graphical representation of the equation y is equal to 7x. So let's go ahead and look at example 2. The work that you're going to be doing in chapter 6.9, if you don't have the vocabulary, you can't do it. Please learn the vocabulary. Question says, find k if y varies directly with x and y is 6 when x is 3. Write the equation that expresses the variation. And that sounds scary because you've never done anything like this before. Find k if y varies directly with x. Find k if y varies directly with x. Varies directly. You have direct variation. What is the representation for direct variation? Y is equal to kx. This is the formula or the form of the equation of direct variation that you're going to use. This is what your first sentence tells you. It says find k if y varies directly with x. The tells you're using varies directly means you have to use the direct variation equation. It says y varies directly with x. Let me actually write this out here. Read this as y varies directly with x. Instead of saying y is equal to kx, you can say y varies directly with x. Totally the same meaning in those two expressions. It says find k if y varies directly with x and y is equal to 6. Y is equal to 6 when x is equal to 3. What did you just get given here? 2 values. It says find k when y is 6 and x is 3. Substitute in your values for the variable. Y is 6. We want to find out what k is. X is 3. How are we going to solve for k? Divide both sides of that equation by 3. And you have k is equal to 2. What is k? K is the constant of variation. Your next question says, write the equation that expresses the variation. It's language. Find k if y varies directly with x. When something says y varies directly with x, you know that you have to use this equation. Because this equation right here means y varies directly with x. You've been given 2 pieces of information. You've been given y is 6 and x is 3. So you substitute for k. So now you have what the value is for k. So that means that your equation becomes y is equal to 2x. Two steps, two separate things that you have going on here. 3 actually. First off, you have to remember and realize that if they talk about direct variation or something, y varying directly with x, that they're asking you to use this you have to use the direct variation equation here. And you have to understand that they're going to give you pieces of information that let you calculate what k is. K never changes, that's why they call it a constant. God is constant, He never changes. K is constant, it never changes, it's that multiplier. If x goes up, y goes up proportionally. There's that direct relationship between what x does, that's what y does. X goes up, y goes up. X goes up high, y goes up really high because that constant of variation does not change. And if once you know what your constant of variation is, you simply substitute that in and you have your equation for the graph of the relationship that's been described here. Okay? Let's look at example 3 and see what we have. This says, if, on page 259, if y varies directly with x and y is equal to 8 when x is equal to 4/5 and y is equal to 8 when x is equal to 4/5, find y when x is equal to 3. Find y when x is equal to 3. Now I can remember eons ago when I was trying to figure out things like this, and I got all tangled up, messed up, turned around with the vocabulary. This is not a hard problem, but it's a multi-step problem, and you have to be able to understand exactly what they're asking you to do. So let's look at this. If y varies directly with x and y is 8 when x is 4/5, find y when x is 3. First off, what are we seeing? Y varies directly with x. Y varies directly with x means that you have to use this equation. This says y varies directly with x. What's it mean to say you have direct variation? Is that y is going to be a multiple of x. It's that same multiple all the time, whether the multiple is 1 or 5 or 25 or 200 or 4/5 or minus 1/3. I'm sorry, or positive 1/3. But there's always going to be a relationship that is consistent between the x and the y. And in order to be able to find other values or come up with equations, you have to figure out what k is. So the first thing you're going to have to do is find k somehow. Find k somehow. How's that for horrid English? How can we find k? Well, we are given this piece of information here. Y is 8 when x is 4/5. Y is 8 when x is 4/5. This is how we figure out what k is equal to. How are we going to isolate k by itself? If you multiply a rational number by its reciprocal, that product is always equal to 1. So what are we going to do? We're going to multiply both sides of this equation by 5/4. 4's cancel, 5's cancel. We can reduce here 5/4 times 8. We have a factor of 4 that cancels, leaving us a 2 in the numerator. So we have k is equal to 10. Do you see how that happens? All we did was substitute in y is 8, x is 4/5, multiplied both sides by the reciprocal, cancel common factors, and we now know that k is equal to 12. Okay. I'm sorry, k is equal to 10. What do we do now? Now we look at what our problem is actually asking for us. What are they asking us for? Find y when x is equal to 3. We want to find y when x is equal to 3. Y when x is equal to 3. Why did I go ahead and put that 10 in? Because k is a constant. K doesn't change. Once you determine what k is for the problem that you're working at, you don't use k anymore, you use the number. Find y when x is 3. Your constant of variation is 10. So y is equal to 30. And that's what you need to do. You have these, take a bite of the problem at a time. Y varies directly with x tells me that you have to use the formula y is equal to kx. Y is 8 when x is 4/5 tells me to substitute in y and x so that I can come up with my constant of variation. Once you have a value for your constant of variation, then you can say, okay, what's y going to be if x is something? What's x going to be if y is something? Because you have already calculated what k is, and that number's not going to change. Okay? Promise you, the more you work with these, the easier they become. I want to go ahead and look on page 260 now. Example 4 says, if y varies directly with x and y is equal to 2/3 when x is 10, find y when x is equal to 7 1/2. They have to have this piece of information in the beginning. It says if y varies directly with x. So you know that y varies directly with x. Because I just briefly touched on this at the very beginning of the lecture. I said there's also something called inverse variation. If they had said y varies inversely with x, you would use this equation here. So it's very important that they say if y varies directly as x and y is equal to 2/3 when x is equal to 10, you're going to use that to find your constant of variation. Y is equal to 2/3 when x is equal to 10. Okay? See, I switched it around, said 10k. I like to have my number first, but let me stay consistent. Y is 2/3 when x is equal to 10. We have to find our k value. How are we going to do this? Well, we want to isolate k. It's been multiplied by 10, so we can divide both sides of the equation by 10. This is an example where it's nice for you to remember that multiplying by the reciprocal is the same as dividing by, because look at this, you've got what they call a compound fraction here. It's just not convenient to do 2/3 divided by 10. So rather than dividing both sides of the equation by 10, we're going to multiply both sides of this equation by the reciprocal of 10, which is 1/10. So we're going to multiply both sides of the equation by 1/10. Our 2's cancel. A factor of 2 cancels, which tells us that our constant of variation this time is very small. It's 1/15, which is the slope, right? So that means just very, very gradually over time, you're going to see an increase in your y value. Now, find y when x is equal to 7.5. 7.5 rather. What piece of information do we have? We have k is equal to 1/15. So now we go on to the final stage of our problem. And we say y is equal to kx, which I promptly erased. Y is equal to kx, or y varies directly as x. Find y when x is equal to 7.5. Is equal to 7/2. Do we want to have 1/15 times 7.5? No, this is why I say just keep improper fractions. 7.5 is 15/2. So what value does y have? Y is equal to 1/2, because our factors of 15 have canceled. That's all you do. You're going to have problems like this over and over again. It says something varies directly as x. Tells you to use this formula. It's going to give you values for x and y that will let you determine what your constant of variation is. Then you're going to use that constant of variation to find out some more information. Okay? There's one more illustration here that I just want to touch on for you. This is actually from physics, from some basic physics that at some point you might learn. But let me read you what our book says. A relation is linear if it can be put in the standard form of a line, ax plus by is equal to c. So what I showed you. So it's going to describe certain lines, and specifically it's going to describe lines that pass through the origin. That's what they're saying. Y is equal to kx, and k is greater than 0. So they are lines that go through the origin that have a positive slope. But sometimes it also relates to other relations, and these relations are not necessarily a function. For example, this says the distance that an object falls varies directly with the square of the time. If an object falls 64 feet in 2 seconds, how far does it fall in 5 seconds? So this says the distance that an object falls. So distance that an object falls varies directly as, well, with what? The square of the time. You know what you're looking at right here? Varies directly. Anytime you see varies directly, that means that you're going to use the specific formula y is equal to kx, because y is equal to kx says y varies directly with x. Now, what is y going to be here? What is x going to be? This says distance varies directly with the square of the time. Y varies directly with the square of the time. Y is distance. So the distance varies directly with the square of the time. We're going to say t is equal to time. Right here's our formula. The distance of a falling object, the distance that an object falls, varies directly with the square of the time. If an object falls 64 feet in 2 seconds, how far does it fall in 5 seconds? Distance is 64 feet in 2 seconds. Okay? We have to find our constant of variation. 64 is equal to k times 2 squared. 64 is equal to k times 4. Our constant of variation is equal to 16. You see that? We haven't done anything differently than what we've done so far. Our constant of variation is equal to 16. All we did was substitute in for d and for t, and you had me help you say, okay, if y varies directly as x, then we can say that the distance varies directly with the square of the time. And we now have this important piece of information that tells us that our constant of variation is 16. So an object falls 64 feet in 2 seconds. And we want to know how far does that object fall in 5 seconds. So here's our formula. The distance, we want to know how far that is, in what amount of time? In 5 seconds. Our constant of variation was 16. Distance is equal to 16 times our time squared. Distance is 16 times 25. Look at that. In 2 seconds, the object fell 64 feet. So you might think, okay, 1 second is 32 feet. 32 feet. 5 seconds, 160 feet might be how far you think you had fallen, just without paying attention to what this problem says. But this 400 is way different than 160. So this is falling much more rapidly. So what they're wanting you to see is this is not a linear relationship. There's not a direct relationship with the distance that the object falls. And it's because we've got this square in here. That's what the difference is. What is direct variation when it's a line? Y is equal to kx. That's a linear relationship because the exponent is 1. This one is not linear because the exponent is a 2. I took the time to go through this problem because this is one of the examples that they gave to you. You're not going to have a whole lot of things like that because they're wanting you to see linear relationships. But it's still important for you to see that we can have a constant of variation that stays the same, but it's not a linear relationship. What this would look like roughly if you're graphing it is it's going to go, because the y value is increasing much more rapidly than the x value is increasing. That's the end of our lecture on direct variation, and I'll see you next time. What we're doing next time is we are graphing linear inequalities, and this is a lot of fun. This is where you get to shade graphs on your, you're going to graph more than one line on your Cartesian coordinate system, and you shade in the solution. It's really sort of fun. See you next time.